was just doing work on your project, so there's nothing for us to go over today on that. I'm bouncing between many screens, so someone had put a chat in here. Did you have a question? All right. Let me, you guys should be seeing. Sorry, I've got, right now this Zoom is covering up my screen to start the, hang with me for just a minute here. All right. Hopefully everybody has received the Excel files that I sent out. All right, so what we're going to do today is we're going to talk about different ways to find a best location, optimize locations when you're going to add a department, add a machine, or add a facility, a new facility somewhere. This has a lot of kind of interesting applications. And for those of you who like the more mathematical side of courses like this, then this will fit into your interest a little bit more. All right. So what we're going to talk about today is some graphical algorithms to help optimize locating of facilities, departments, or machines. As I said, where should you place a new facility, a new department, or a new machine that would be would provide the best solution? We're going to do it using graphical methods to begin with. Then we're going to use Excel Solver. I'll show you some routines that I put together. I copied them out of the textbook. The nice thing will be is that you can use the spreadsheet that I provided on the exam as a tool. So you want to make sure you pay close attention, follow through, and ask questions about it as we go through so that you'll be able to use the tool efficiently during the exam. And then we'll go into an algorithm that will, just to show you other types of algorithms that may exist. Other people have done research and applied techniques to optimizing, in this case, a sequence of machine layout. Right? We did that with the pairwise, where we tried to find the best sequence of, for the example in the book was 4 different A, B, C, and D. So what was the best sequence to order these? Well, we're going to look at another routine for optimizing machine layout if you're doing it in a sequence. Some of you may end up doing that as a production engineer. You'll be asked to put together a small work cell and to come up with a sequence of machines that will optimize the results. Okay? All right, so graphical methods or mathematical methods, different things they can do. We can, excuse me. I said we can optimize a location, a department, or a single piece of equipment within a department. So when we're talking about optimizing a location, where might be the best area to locate a new airport that minimizes the amount of travel that people will have? given the populations in different areas. Where should a school be located? Where would be the optimal location for a new school in a community to minimize the amount of travel distance for the parents and the kids? If you're going to put in a new wireless tower, where would be the best location for the tower to maximize its coverage of a certain area to people in a certain area? Sewage treatment plants. Where would be the best place to locate a sewage treatment plant so it's as far away as possible from population? Let's see what else we have here. How about a post office? So it provides service to the maximum number of people in a certain community. Same thing with a hospital or a library. Where should we locate a fire station so it has the fastest response time to the areas that most likely will have fires or need some kind of help? Where should ballot boxes be located to minimize the travel time and maximize the number of people they service? A couple of military applications. Where would be the best place for a sniper to be located to cover the certain areas to provide the best coverage? A military strike team is one of the examples in a textbook where should we locate a military strike team so it has the minimum amount of travel distance in case it's needed. So there's a lot of different applications for what we're going to cover today. For a department, so you're going to add a new department. So we're going to figure out how you might be able to locate a new department within an existing building that minimizes the travel distance to different departments based on the distance traveled and the number of loads that need to be moved. And the other thing, the last thing, will be optimizing a certain machine within an existing work area, where you might want to minimize a single machine. We're going to start with a single machine that will minimize the distance and the number of loads to all the other machines. So once you finish machining something, you have certain loads that have to travel somewhere else. Where would be the best place to put it when it has to go to multiple locations? And you want to minimize the total travel distance. And what if you're locating more than one machine in a work area? Where would be the best place to locate the two or more machines? Well, what we're going to just cover in this class is just two machines, but you could change the model that you've received and make it for multiple machines. Any questions so far? All right. Okay, so there's three ways to look at these models. The first one, the most logical one, is mini-sum. There's mini-sum, mini-max, and maxi-min. The mini-sum is going to calculate if you find a new location, if you have, in fact, I think I have it on the next page. Here, I've got an example we can use. If you want to locate a single machine here, this machine is going to travel. It's going to have loads when it's done machining a part. It's got to travel this far in an X and Y direction times so many loads, travel to this point in an X and Y direction times so many loads, and so on and so on and so on. It travels, if I locate it here, it's got to travel to these locations so many times, so many loads. Okay? I can calculate the total sum. I can calculate the sum of all those load times distance. And I can come up with a value for the load times distance. So the sum of the load times distance for that location. What mini-sum will do is it's going to, the algorithm will keep, what if it was here instead? What if it was here instead? It'll do the same calculations of distance times load, and then it'll pick the best location that has the minimum sum of all these possible locations within this building. So that's what mini-sum will be. Let me erase this. Whoops, excuse me, I'm trying to erase this right now. Excuse me a second while I try to make this work. All right, there we go. All right, so let me clean this up. We're going to come back to this same layout. So that's the mini-sum. In other words, if I were to put the point right at one spot, what would be the sum of the load times distance to all these other points? Then what if I moved it to a different spot? What would be the sum of the load times distance? Well, we're going to let Excel do that for us, and it'll be able to, in a very small amount of time, it'll be able to determine the best location by constantly changing where that point, the new machine location will be. So that's Minimax. Minimizes, so what it can do is minimize the travel distance for an emergency response. Where should I locate it? So it's the minimum amount of distance to the maximum areas. Minimize the distance workers have to travel to a portable restroom. Where should I locate that new restroom? Those points I was pointing out. What if it was a restroom? Where should I locate it so that the total amount of time that workers have to travel will be minimized, the sum of the traveled load times distance, and what we just went through, a new machine to an existing machines that are already there. I'm sorry, that was mini-sum. Then there's mini-max. Then there's mini-max. What mini-max does is it minimizes the longest distance from for a location. So what does that mean? We go back to that other item. So if I were to locate here, for this location, the distance from here to 0.5, from here to 0.2, and so on and so on. What I'm going to do is the algorithm is going to find the maximum of these, the longest travel distance. If I were to locate it here, out of all these points, which one of these points is going to be the longest travel distance, the maximum? And then the algorithm's going to try to find the best location that will have the minimum of the value. So it'll be the minimum value of the maximum distance from these points. Now, when we get into this a little bit more and actually go through that, I'll re-explain what that means. But 8 questions on that. There's got to be a question.
Actually, I do. By load, do you mean flow?
So load is the number of trips, the number of travel times you go. So there's distance, that's easy, right? You travel so many feet. The loads is the number of times you travel so many feet.
Okay.
So what Minimax is going to do
And you're
is
trying
this.
to optimize. I guess the best way to get.
Yeah.
Listen,
So
you keep cutting off, or maybe it's my internet, but it keeps cutting off.
is anyone else having trouble with me cutting out?
Yeah, when I logged in, I don't know if you're taking note, but I was here and it took like a couple minutes.
Couple of minutes
Yeah,
for you to
it
log
keeps,
in.
no, the audio
Oh,
would cut in and out, but it's just random.
how about other people?
Mine's okay.
Yeah. So it sounds like there might be one or two of you that are having a difficulty. Generally, it sounds like it's working. Am I wrong on that? Okay. So it sounds like some of you may have you may have connection problems. There's no way I can tell for sure whether it's you or me, but it sounds like most people are doing okay with it. So,
Just keep.
all right. But feel free, Michael, feel free to ask me to repeat something if it does cut out. And I'll try to talk a little slower to make it easier too. So again, sure. Minimax. So what it's going to do is it's going to find a point here. So I'm going to put a new restroom right here. What's the maximum distance that somebody's going to have to travel to get to that restroom? Well, from here, maximum, I'm going to take all the travel distance from all 5 of these points. And then I'm going to, the algorithm is going to find the minimum. The maximum distance out of all 5 of the possible distances. Then it's going to try, what about this point? What about this point? What about this point? So on and so on. And then it's going to find the one location that'll have the minimum of the maximum travel distance. And again, we're going to cover this in more detail when we actually do the algorithm. So you'll see that again. That can be confusing. So that's a mini-max. We have mini-sum, where we're going to sum up the load times distance for all 5 points, and then find the location that will have the smallest of that, the minimum. Then mini-max is we're going to calculate from to all 5 points, we're going to calculate the maximum distance and select the one distance that's the maximum. And then we're going to try another point, and we're going to select the one location that has the minimum maximum distance. And then the last one will be maxi-min. And what that does is it tries to locate, it's going to help you to find a distance where to locate something that will be obnoxious or offensive to existing locations. So it maximizes the minimum distance between obnoxious and offensive new locations to existing locations. So let's say you want it, it'll maximize the minimum distance to a waste disposal site or to a prison. If I locate it here, what's the minimum distance to here? Well, it's there. What's the minimum distance to 3? Here. What's the minimum distance to 1? Well, it's here. What's the minimum distance to 5? Will be here to here. So what it's going to do is after it calculates how far it has to travel to each one of these, then it's going to find the minimum out of this. There's how many possible? 1, 2, 3, 4, 5. There's 5 travel distances. What the algorithm is going to do is pick out the minimum one, the shortest. Then it's going to do the same thing with another point, and it's going to find the travel distance to all 5 of these points, and it's going to find the minimum travel distance again. And then it's going to keep doing that to cover this entire area until then it's going to select the one that has the farthest of the closest locations, the farthest of the minimum. That's a little bit harder to conceptualize. But keep in mind, when you have something like a waste disposal site, you want it as far away from communities as you can, right? But there could be many different locations for that. So what you want to do is you want to, if I were to locate it in this particular location, what's the closest housing community? Well, what if I moved it over here? What's the closest housing community? So what you keep doing is you keep moving the location till you find where the closest value for any particular location is the highest value. Interesting, I found this too. I added this today. In gaming theory, they use this to determine if you're going to lose money. What solution will minimize how much you lose? In other words, it'll provide you with the best of the worst possible cases you're going to lose money. So what this algorithm can do is determine the minimum loss, the best of the worst. The minimum of losing money. All right, so my guess, I can't see faces. My guess is that this was still somewhat confusing. I suggest you we'll cover this next week again, so you'll get a chance to talk about it a little bit more, so you understand it better. But I also suggest you read the textbook, all right? So this is a difficult one to get your arms around. Minimax is a little bit easier. And when I explain, which I also believe is next week's lecture, when I explain this with the algorithm, it'll make a lot more sense. This one, we're actually not going, I don't have a routine for that. The book doesn't provide one, and I don't have a Excel spreadsheet for that. All right, questions so far? All right. All right, now, in this model, we've been figuring the distance, let's say from this point, in a rectilinear fashion, x plus y travel distance, the absolute value of x, how many x units, doesn't matter whether they're positive or negative, it's the absolute value of x and the absolute value of y, and we add them together. That's called rectilinear distances. That's one way to measure distances. The paths are orthogonal, x and y, and you add the absolute difference between the x and y coordinates. There's a name for it. It's called the Manhattan or taxicab distance. And the reason they call it that is because a taxi in New York City, in Manhattan, a taxi, it's laid out in a grid. The city is laid out in a grid. So the travel distance by a taxi is always in the x and y direction. To get from here to here is going to be this and this. That's the distance, x, y. Then another method that we're going to look at is the Euclidean method, which is line of sight, called line of sight. It's a straight line. So what it does is it finds the distance from here to P2 is not going to be this plus this. It's going to be a straight line of sight from here to here. So it's the hypotenuse of the triangle. So you might remember c squared equals a squared plus b squared. And that's what we're going to be using. This will be A, this will be B. So if we want to find the value for line of sight, it's going to be the square root of A squared plus B squared. Actually, we're going to look at it from two perspectives. In one case, it'll get the same result, slightly different calculations. C will either be c squared, or we'll either calculate c as equal to the square root of a squared plus b squared, or we'll look at it from c squared. It's called the squared Euclidean, and that's equal a squared plus b squared. So we're either going to calculate c squared or c. All right, that's one way to measure it, line of sight. When you transmit an electrical signal, like from a cell tower, you fire a bullet, then it follows line of sight. It doesn't go around corners and make bends and turns. So that will be straight line applications. By the way, rectilinear, certainly in R, when we're talking about facility planning, is the most common. Because in most cases, inside a building, you're not able to walk in a straight line because of aisles, machine locations. Things are usually laid out in some kind of a grid. Most movement is in an X and Y direction and not line of sight, usually. Then there's the Chevanez distances. Chebyshev, I mispronounce this all the time. Chebyshev distances, where it travels rectilinear, but it also includes vertical, X, Y, and Z. We won't be covering that at all. So 3 methods. And then finally, the fourth method is the actual travel distance. That's something you get when you plug in your map, you use Google Maps or Waze or something like that. It'll give you the actual distance, which can include a variety of different traveling modes. So the actual travel distance, or rectilinear, or Euclidean. We're going to use rectilinear and Euclidean to solve some of these location problems. Any questions? All right. Okay, so let's go into some rectilinear. First, we'll do some graphical methods, and then we'll go ahead and we'll use Excel to do some optimization. All right, so what we can do with the rectilinear, we're going to do that first. And then next week, we're going to do Euclidean methods. What we're going to do is optimize either, we're going to optimize either one or two more, but we're going to do two, one or two new locations to existing multiple locations. Right? So we're going to start with the mini sum. And that's going to be, we're going to sum up, we're going to find a single point, a single location, and then we're going to sum up the loads, in other words, the number of times it travels, times the distance to each point. We're going to sum up all, how many, we have 5 points here. We're going to calculate the sum of the distance in the X plus the distance in the Y direction from our new point. Here's our new point, X and Y. An existing point like P4 is going to be A1, B1. Well, this is A4, B4. All right, because it's point 4. So what we're going to do is we're going to calculate the distance. So we're going to take the absolute value in the x direction plus the absolute value in the y direction. And we're going to multiply it by omega, which is the number of loads. And that'll give us the load distance just to 0.4. Well, we're going to do the same for points 1 through 5. And we're going to sum them all up. Then when we use Excel, what Excel will do is it will very quickly calculate it'll do multiple points, not just here, but here, plus here, plus here, plus here, plus here. And it'll calculate the sum of the loads times distance at each one of those points. And then finally, it'll select the best location, which might be this, that has the minimum load times distance. All right? So just for reference, the A's and B's in the equation here are the existing locations. X and Y is your new location, and omega is the weight. Now you can make your origin an arbitrary point. For a building, the sensible thing would be to make this your one corner of the building. Okay, so that's what we're going to be doing to begin with. Okay, now I call these quick and dirty because you can do these relatively easy and relatively fast. Relatively quick and relatively fast, but they're not optimization routines per se. That's where the dirty part comes in. All right? So this first method is called the median condition method. So what we're going to do is we're going to order the machines. We're going to find an X and Y direction that approximates the load times distance. Let me see how we're going to order the X and Y coordinates. I'll walk you through the technique. We're going to order the machines by X and Y coordinates and find the coordinates that are half the sum of the weights in the X and the Y direction. And that will be the median, not the middle, not the mode, but it'll be the median condition. We're not going to consider travel costs, which is generally the case. Travel costs are almost always the same, whether the only time it might be different is if you have to have a specialized piece of equipment to move things around. Okay? So here's existing machine locations. That's the same image we've seen so far several times. All right? Now, here's the loads, trips or loads. Go back to what Michael was asking, per day. So we want to find the location in the X and Y that will have approximately half of these loads, a point that'll take us to about half the loads. So here's the routine. So let's look at the X direction first. Now we're going to order them in sequence in the X direction. So notice that P1, its X is at 1, P2 is X is at 6, P3 is 2, P4 is 3, P5 is 8. All right? So what I'm going to do is I'm going to order them in sequence. So 1, the closest one to my origin is P1 in the X direction. So there's 1. The next closest one is 3. That's at X equals 2. The next one would be 4, where x is equal to 3. So see, as I move in this direction, I'm just looking at the x value. Here's 1. Here's x equals 2, x equals 3, x equals, let's see, 1, 2, 3. Oh yeah, okay, and x equals 6 and x equals 8. All right, so the sequence is going to be 1, 3, 4, 2, 5. 1, 3, 4, 2, 5. That's the sequence of x's. Now the weight for 1 is 10. The weight for 3 is 25. The weight for 4 is 20, and so on and so on. So now what I want to do, how much is the sum of all the weights? Well, it's 35, 55, 75, 80, there's 100. The sum of the weights is 100. 100 loads, or 100 trips. So halfway of that, half is equal to 50 trips. So in the x direction, if I locate it at 1, that'll only cover 10 trips, not 50 trips. If I make it 2, that'll cover 10 and 25. This covers 35 trips total. If I make the x value for my new machine at 3, then that will cover 25, 45, 55 trips. If I make it at 6, x equal to 6, then that will be 75 total trips. And then finally at 8, it'll be the whole 100 trips. So if I make x equals to 3, that's going to be closest to half the number of trips at x equals 3. Okay? So 1, 2, 3. So x is going to be here. Same thing with y. Now, as I go from 0, the first y I hit is at P1. The second y I hit is P2. The third y I hit is P5. The fourth is P4. And the fifth is P3. Now, the other way you can do that is just go to the y values. So P1 is the smallest y. P2 is the next smallest. P5 is the next smallest after that. Sorry. P5 is the next smallest, and then 4 and 8. I mean 4 and 3. So that's what you see right here. So that's the sequence of y's. Now I do the same loads. If y is equal to 1, then the load is 10, right here. If for y is equal to 2, the load is 20. Y is equal to 4, the load is hold on a sec. Because y is equal to 5, the load is 25. Y is equal to 4, the load's 20, and then 25 when y is equal to 3. So I start the same sequence. If y is equal to 1, then so there's 10, the load is 10. If y is equal to, at machine 2, the load is a sum of 30. If I add machine 5, it's 55, and 75, and then 100. So again, this is my median value. It's the closest to 50 trips. So what I'm going to pick is for machine 5, y is equal to 4. So the best location with this fast, easy to use method is 3 and 4. So it's right here. X is equal to 3 and 4. Questions on this process? All right, so this is one, it looks so simple, but I suggest that you practice doing this for the exam. What seems simple can get very confusing if you're looking at it or trying it for the first time during the exam. You'll end up putting too much time into trying to figure it out. So make sure you go through the example and attempt this problem. And what I suggest is you know what you're looking for. Just take these numbers, write them down on a piece of paper. You could even hand copy this drawing and then try to solve it without looking at the result. You know where it belongs, but see if you can come up with it. See if you can create this table. All right? Any questions on this?
Yeah. So the table is what we need to create, right? The X and Y coordinate tables.
Yeah, well, yes. Now you may be able to eyeball it, but if you do it by the X and Y, you'll feel confident you've got it done. So you would be given this information, and from this information, the locations, you can create this. So that would be given to you. So what you need to do is figure out where the optimum location is. And the way that the book points out the uses method is using this, you would create this table. Other questions on this? How to use it, what it's for? Okay. So this is approximately the middle location for locating your new machine based on loads and distance. It's not optimal, but it's somewhat close. Okay, no more questions? All right. Here's another method. We'll do this and then we'll take a few minute break. Now, if you have a situation, this would be pretty common actually, where your new machine can only go in several different locations. Maybe you're limited by the type of process. Maybe you're limited because there's structural beams in the way. So you go out to work area, you've got to put a new machine in. Let's say into this work area, this room. And at first glance, you know that you can only put it in these 3 locations. You can't put it over here, you can't put it there, you can't put it there, you can't put it there. So here's another easy way to figure out which of these 3 is going to be your best location. And it's pretty straightforward. It's just calculating the load times distance for each location. That's all it is. By the way, the reason this is highlighted in yellow is on your, if anyone's got these slides, on the slides it said 440. I realized the mistake just before class today and I corrected it to 450. So how did I come up with that? This is the, in the X direction, let's take this one location, 3 and 5. Let's just take this one location for sample calculations. So what I did was I figured the distance from, let's see, from here to here is 2, it's 5. Let's see, I'm just trying to, that doesn't look like 2 to me. So the distance from, let's say, here to 1, and 1. So that's actually right there. Okay, so what I did was I just calculated for this single value, this single location, the load times distance. It's pretty straightforward. So that would actually be how many in the x direction? It's going 3. So it's going 2 in the x direction, and that's this. So in the x direction, it's going 2, and there's 10 loads, 2 times 10. In the x direction to number 2 is here. So that's 6 minus 3 is 3, and there's 20 loads. So the way the book shows it is that we go through and we calculate the x direction individually and the y direction individually. I don't see the point in doing that. What I would do for this is I would just add up the distance, x and y distance added together. It's easy to count, and multiply it by the load. So I would actually do it as 6 times 10. But what you'll end up with is 450 for the total load times distance of Q1 to all the 5 existing points. 450. Then for this one, if I did the same load times distance, it comes to 460. For this one, it comes to 470. And this is the smallest. So I've only got 3 possible locations. I would choose this one. Not a lot of magic to this solution. But this would be a situation if you had a limited number of possible locations. Questions on this routine? Okay, pretty straightforward. All right, it's 3:09. Let's see. So we've been here an hour and 10 minutes. Why don't we take a 5-minute stretch, hit the restroom break, and then I'll go ahead and continue on with the lecture. So it's 3:09 right now, and we'll start back at 3:15.